Hi guys and gals, it's time to have a look at a few videos on surface area and volume, and today we're going to kick the ball off by having a look at area. Okay, now what we should do firstly is have a look at some formulae for various shapes, the areas of those shapes, and let's just go through them one by one. I think you know the one for a square. That's just basically L squared. It's length by width, but the width is the same as the length, and this little dash here indicates that all those four sides are equal. And if we know that this is a right angle here, well, we got ourselves a square, and the area is L squared. Yes, check-a-rooney. For a rectangle, it's the same sort of thing. It's just the length by the width, except that this side is the same as this side, that side is the same as that side, hence the two dashes here, the one dash there, and we know that we have a right angle in here. It's not drawn, but it is a right angle, and the area is the length times width. Now you know that, don't you? Of course you do. And here's another old faithful down here, the good old triangle. My goodness, we know that one, don't we? It's the area is the half of the base times the vertical height. That's the perpendicular height from the base. Right? That's, you know that one very, very well. Okay, over the screen we go. Now this is a nice little beastie, this one. Trapezium. That's a Latin word which means little table. I have no idea what the significance of that is or how it ever got that name. However, let's do the area of it, and it's basically the average length of the parallel sides, which means add them up and then divide by 2 times the vertical height. Okay, half of A plus B times H. Yes, very good. Circle. Circle is pi r squared. Everybody knows that one. I hope you do know that one. If you don't know it, please learn it because you need it. Pi r squared. Yeah. Now this is a very interesting one, this parallelogram. This is just simply the base times the vertical height. And you know, ladies and gentlemen, the way that I remember this parallelogram one is very, very simple. In my mind, I get some scissors and I snip up here, right? And I grab that triangle that I've just cut off and I put it over here. And it sits there like that. So in effect, I've converted that to a rectangle, which has the same base here, the same base B, transfer that bit over to that bit, same base B and same vertical height H, so therefore it's easy to remember the formula for the area of a parallelogram. It's just similar to a rectangle, okay? You got that? B times H, base times vertical height, okay? Now a few more. We're getting into the exotic ones now. This is not so exotic. This is just the area of a sector or a pizza slice. Okay, so it's really the area of a circle times the fraction that this sector is of a circle, which is the same fraction that this angle theta is of the full 360 degrees in a circle. So you'd say the area of this sector is pi r squared, e.g. area of a circle, times the fraction that theta is of the full 360 degrees. There you go. Theta over 360 times pi r squared. Yeah? Now, rhombus, this is very interesting. What's a rhombus? Well, ladies and gentlemen, it's a four-sided figure where all the lengths are the same. See these dashes here? All the lengths are the same, but it's not a square because these angles here are not right angles. So it's kind of like a bent square. You know, you've sort of bent the square over, okay? Now the area of a rhombus is found by multiplying the diagonal lengths together and then dividing by 2. Half x times y. How very interesting. Did you know that one? Well, I have to admit to you, I didn't know that one, so now I do, and I'm fascinated to learn it, okay? So, you know, even an old git like me can learn something new every day, and I love to learn. So now here's the last one. This is an ellipse. This is a very interesting one. It's just like the formula for the area of a circle, except, of course, an ellipse is a squashed circle, like an egg. So instead of pi r squared, you don't have r anymore. You have a, which is called the x semi-axis, and you have b, which is called the y semi-axis. and then you just say pi a times b. How interesting. It's sort of like pi r squared, except you can't have r's anymore because it's all bent out of shape. But the formula is very similar, isn't it? So pi a b for you and me. Now, this is a small little sentence, but it's extremely important, so please take note. Measurements must be in the same unit of length before substituting into an area formula. Oh boy, is that important. You must be consistent. Don't mix up your units, otherwise you end up in more trouble than I don't know who. Now, this is also an extremely interesting new formula which I'm delighted to share with you. The alternative way to find the area of a triangle. Now guys, if you know all three side lengths, right? If you know all three side lengths but you do not know the vertical height, this is where this formula comes into its own. It's called Heron's formula. H-E-R-O-N, Heron's formula. Now, what you do is firstly you work out what's called the semi-perimeter, which is just add up all the lengths of the three sides and then divide by 2. Okay, semi means half. Right, so half of the perimeter, the semi-perimeter. Then you plug that into this amazing formula. The area, A, is equal to the square root of S, that's the semi-perimeter thingy, right? S times S minus A times S minus B times S minus C, and you've got it. You've got your area. Isn't that fascinating? I know, that's Heron's formula. So there's a new one. Now, I hope you learned something new in all that, because it's great to learn. Now, let's do some of these now. Come on. Let's get our thinking caps on. Find the area. Areas of the following plane figures correct to 2 decimal places. Remember, we've got to do this to 2 decimal places, guys, okay? Now, these are in centimetres. Okay. Number A. Triangle, no perpendicular height indicated. So we're going to use this beastie up here. Heron's formula, yes? Okay, let's go with it. Using Heron's formula, we've got the semi-perimeter is 3 plus 5 plus 6, all divided by 2, which, now let's make sure I haven't made a mistake. 3 and 5 is 8 and 6 are 14. 14 over 2 is 7, that's right. Now we'll plug that 7 into our amazing looking square rooty formula now, and there it is. Now you better see if you agree with me. That's S minus the 3, S minus the 5, S minus the 6, good, 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 and see how we go with that. Now is that right? 7 times 4, that's right, times 2 times 1, that's right, isn't it? Very excellent. 7 4s are 28, 2 28s are 56, yes, square root of 56, but 2 decimal places needed. Ha ha, 7.48 square centimetres, because these are in centimetres, alright? Make sure you don't get mucked up with your units. Excellent, alright, that's that one done. Right, will we do B? Come on, we'll do it. That's a very easy one. That's an ellipse, it's pi AB, remember? So therefore, we do that. Pi times 5 times 2, 10 pi, which would be, apple of my eye, flying high, my oh my, look what we got from the calculator, 31.42, and again, that's square centimetres, okay? Very excellent. Right, the third one's a pizza slice. We know what to do, don't we? Of course we do. It is pi r squared times 40 over 360. Yes? 40 over 360 times pi times 15 squared, and I think we might have to go over this. Oh no, we might not have to go over the screen. Is that right? 25 pi. I must have worked it out. 4 into 36 goes 9. Oh yes, and 15 squared is 225. And 9 into 225 must go 25 times. If we do the decimal places, we get 78.54 square centimetres. Yes? Excellent. All right, let's keep going. Now, we've got to think about composite figures. Now, composite figures are just shapes kind of like where you have more than one shape to consider within them, like a bit of a circle and a bit of a square, that kind of thing, yeah? And it's easy to work them out if you just sort of keep your head and sort of use your imagination a bit, you can work them out. So combinations of simple figures, that's what they are. The area of a composite figure can be calculated by either calculating the sum of the areas of the simple figures that make up the composite figure, or calculating the area of a larger shape and then subtracting the extra area involved. Okay, now I'll give you an example of both and then we'll have some fun together. Now, this one is an example of this first dot point here, and this one is an example of this second dot point here. You actually don't have to do this one by using this second dot point approach, but it's just quicker and easier if you do, okay? I'll show you what I mean in a moment. Let's do A today. Hooray. Now, come on, have a look. How would you do that? How would you do that? Yes? Made up your mind? Alright, well I'll show you what I did. I converted it into, in my mind, an upper triangle, which I've just outlined in red for you, and a green triangle outlined there, the bottom one outlined in green. Yeah? So, let's work out the areas of each of those triangles and then add up to get the area of the composite shape. Alright? So there's the first one, there's the second one. Now, okay, the area of the shape, yes, is the area of triangle ABC plus the area of triangle ABD, the one underneath. Now, let's just do it now. What have we got? We've got AB is 8, and this one here, this height is 6, that's C to E or E to C, divided by 2, that's the red one done, that's this one. Yes, correct. Now the second one was the base is AB again, which is 8, and then what we're doing below is F, that's F to D is 2, and that's so it's base by times height over 2. Yeah, we're correct, guys, we're correct. So that's 24 plus 8, which gets you 32. 32 square centimetres, yes? Terrific, okay. Alright, now let's do this other one now, and I'll show you what I mean by the doing an overall area and then subtracting, yes, subtracting the area of the smaller shape from the larger shape. Now what am I doing there? I'm working out what the length of A to H is, right? That's that vertical side on the left. Now what is it? Now how did I work that out? Now come on, this is what I did. I said it's 9. Now that's the same, got the same little dash on it, so that's also 9. And then this one here we're told is 2. So 9 down there, plus 2 down there, plus 9 down there gets us 20, right? So we can work that one out, right? Now, have a look at this. That area there which is missing, it's a chunk out of the shape, I've just actually put a little border there just to make out the shape a bit more clearly, but it's actually just space. It's not part of the shape, alright? And I've worked out the area for you. It's basically now, let's just work this out. That's 2 there, right? And this one's 5. Now it's very badly drawn because the 5 looks to be less than the 2. However, we'll just go with it. That double dash, I presume that means 5, goes with that side there with the double dash, the horizontal side there. So the area would be 5 times 2, which would be 10 square centimetres, wouldn't it? Now, why did I work that one out? Well, I'll show you guys. That's the green hashed one. So therefore, what I'm saying to you is the area required is the area of the entire rectangle, which is 20 times 10, which is 200 square centimetres, minus the area of the little bit of space in there, okay? Right? And the area of the space is 10 centimetres, so therefore the total area required is going to be 200 minus 10, which is 190 square centimetres. So you can see that I've worked this one out by doing the area of the entire rectangle, and I'm subtracting the area of this little rectangular bit of space here that's missing. It's a chunk out of the overall rectangle situation here. You see? Okay, now if you didn't want to do it that way, that's fine. You can do it by just adding up shapes like we did over in A. You could maybe draw a little imaginary border there, work out this rectangle here, then you could maybe do the area of, say, this rectangular bit here, like that, and then you could do the area of this last bottom bit here, like that. And you could add those 3 up. But you can see that's 3 steps of working, 3 shapes to work out, to combine, whereas the way I've done it is I only worked out one big one and one little one and subtracted, right, one from the other. So I think it's probably a bit quicker, yeah? Okay, let's see what else we've got for you. Good heavens above, look at this. Well, they might look ugly, but guys, they're really, really simple when you chunk them down, okay? So let's see if we can do E. Have a good look at it now. Yes, confusing, isn't it? Well, do you know what I think? I think that's a subtraction one, because I think, let's just see. I've labelled them with some letters so we can refer to them. Now, what do you think you'd do? Yes, that's the shape we need. That's the shape, that's the bit that's missing from the big triangle here, A, B, C. So what about if we work out A, B, C, right, as an overall big triangle, and then subtract the green hashed triangle B, C, D from that? That'd be a nice efficient way of doing it, wouldn't it? Yes. So therefore the area of triangle ABC is its height, which is 18, times its base, which is 12 divided by 2. And I'm doing a bit of cancelling there. And I get 108 square centimetres. Very, very simple. Now let's do the smaller triangle, BCD. And that is the base, 12, times the height, 5 over 2, which is, yes, cancelling, 6 5s are 30. Good. So now we can work out by subtraction what that funny looking A to B to D to C back to A shape is, yeah? So there it is, it's 108 minus 30, which comes to 78 square centimetres. Done deal, guys. Isn't that great? Yes, give yourself a pat on the back. Now, let's focus on this other beastly looking thing. Now, how would you do it? Come on, have a think. It's a composite shape, absolutely, for sure. Well, I can see a square. I can see a square here, right? And I can see 4 semicircular bits around here, around the outside of the square. Yes? So let me ask you a question. How many equivalent circles do you see there? Well, I see there's a semicircle there, a semicircle there. That's one equivalent circle, and the same thing over here. That's another equivalent circle, isn't it? Right, so let's work out a square plus 2 circles. Well, we have to be very careful to get the radius of the circle correct, all right? What is the radius of the circle? Well, let's see. 14. Of course it is. It's 14. Okay, so that's a bit of a trap if you're not careful. So it's equivalent to 2 circles, radius 14 centimetres, plus 1 square, side length 28 centimetres. No problem. Let's do it. The area required is pi 14 squared times 2, the 2 circles, plus length by width of the square, which is 28 times 28. So now we're done. We're nearly done, and we can just get the trusty calculator out, work it all out. We get 2015.50 square centimetres. I've worked that out to 2 decimal places. Good. Okay, now here's the last two. These look like, one looks good, one looks absolutely diabolical, doesn't it? Well, let's do the good first, shall we? Here's C for you and me. Now, we've got to work out the blue shaded area. So, have you figured out a strategy? These look like they're 8 metres long, these sides, right? Well, I think I'm going to do a subtraction one here, guys. I think I'm going to work out a square and then subtract the area of the circle. Be careful with the radius of the circle, hint, hint. Now, yes, 4 metre radius for the circle, and the area of the square is 8 times 8, or 64 square metres. The area of the circle inside it is pi times 4 squared, which is 50.27 square metres. Alright, now therefore the final knockout punch coming up, we're going to subtract the circle from the square. Very good, and that comes to that, which gets us a final answer of 13.73 square metres. Thank you, Mr. Box. Okay, guys, yeah, very good. Now, I want you to pause the video now and have a go at number D, because it's a particularly confusing looking shape, isn't it? So you pause the video now and come back when you're ready. Okay, you're back? All right. Well, there are a couple of ways of doing this, but I'll show you the way that I eventually worked out, which is probably the most efficient way, I think. Now, the area required, I worked out, guys, let's work out the area of the full, as if it was a full outer circle, all right, without a chunk in it. See, just continue these round in your mind, that border there and that border there, and shade those in as blue in your mind, right? Now, so work out the full outer circle, then subtract the full inner circle. Now, if you did that, you'd have a blue donut, right, going all the way round. Yes, wouldn't you? And then I'm saying, all right, but we've actually got this little chunk out of the right-hand side of it that's missing. So I'm saying if this angle here is 40 degrees, then the area of the shape that we are interested in would be the full donut times only 320 360ths of it. Okay, that's what it'll be, because there's a 40 degree bit missing. Okay, so the proportion of a full donut is just going to be 320 360ths of it. Yes? So therefore the full outer circle is going to be pi times the radius, which is 3 plus 5, comes to 8 squared, minus pi times 3 squared, okay, that's the smaller inner circle, and then times this fraction we've been talking about, okay, 320 360ths, yes, and that comes to that, and when you work it out on the calculator, we will get that, 153.59 square metres, yes? That's the end of the show. Thumbs up to everybody. Now you need to go and do lots and lots of practice and get good at these and get your confidence up. And once you do that, then we'll go on to the next video, which is on surface area. Okay, surface area, that's the area of the surface on various three-dimensional shapes. Okay, fear not, it's lots of fun and you'll get really good at it as well. Okay, thanks for coming, all the best to you, and we'll see you next time.